Entonces, ¿cómo lo hacemos? ¿Qué necesitan de mí?
Teníamos, aquí está el meeting ID.
¿Y eso no lo tengo yo?
No, tienes
Tienes que entrar a Zoom.
a Zoom y
Mándame el link entonces. ¿Tienes mi correo?
sí, pero no lo haces.
No lo tengo.
Ah, ok. Entonces, ¿cómo lo hacemos?
Con el meeting ID.
No sé.
Entonces,
Eso supone que es un correo.
buscar Zoom Join Meeting. A ver. ¿Y
¿Cuál es el Zoom login?
Zoom Meeting. Zoom Join Meeting te va a asegurar. Entonces es 872.
Ajá.
5025. 3116. Lo tenía haciendo mi manual entre las computaciones. Y ya te va a pedir el
¿Sí? No,
Esto pasa.
Sí, que dice.
Es que salió una baja.
Hacer copy. Añadir.
Eso en principio no nos falta, pues ya está
Exacto.
colocada esto
Entonces,
aquí.
no, le digo
Sí,
continue.
exacto.
Ok.
Continue.
Entonces es 600, 502. Puedes poner un nombre ahí para que aparezca.
Entonces, si quieres.
Remember, ok. A ver si.
Sí, falta guardar
Sí,
una
por si
cosa.
acaso.
Vale.
Ok, entonces.
Sí. La cámara que está aquí.
Ok. Bueno. Estoy yo ya. Ok, entonces déjame, nada más voy a compartir mi presentación, nada más para que me digas si la ves o no.
Principio. Eso viene a ser. Supongo que lo tendréis que cambiar cuando os haga falta. Si queréis.
No, en mi caso va a ser corto, déjaselo a él y.
Vale. ¿Veis? Eso lo colocáis luego ya dentro de. Luego se ve y ya está.
Ahí está ya, ¿no?
Sí.
Muy bien.
Así que
Una presentación.
a ver.
Sí, pero a ver,
A ver, ¿funciona?
Sí.
Si no, me puedo quedar aquí.
Sí, ahora.
¿Funcionó?
Sí.
Ok,
Sí,
perfecto.
vale.
Ahí está. Ok.
Exacto.
Ok.
Tarda un poco, pero sí, eso ya aparece ahí. Vale, en principio ya.
Sí, me
Tiene que estar todo.
bueno, compartiré yo por
Sí,
la
que
producción
stop
de
sharing.
10
Sí.
minutos.
Ok. Entonces, stop sharing. A ver, ya dejé de compartir. Vale. ¿Verdad?
Sí, haré una pequeña introducción tuya porque no
Ok.
se diga sobre ti.
Oh, di que soy Luis y se acabó.
Y ya.
No hay más. No hay más.
Okay, so good afternoon, everyone. So thank you for coming. So today we will have our Nanoseminar talk from Professor Luis Ricardez. He's coming from Canada. He will introduce himself later. And we will present briefly a small introductory talk. In this case, it will be about what we are doing at ICN2 in the recently formed artificial intelligence platform. So this is the initiative coming from Severo Ochoa in order to bring support to all ICN2 regarding machine learning and artificial intelligence projects. So just let me introduce. So right now we are two people. It's myself, Andrés, and my partner Francisco Molina. He's a computer scientist, also expert in computer vision. What we usually offer to all the institute is we can help you design, co-design machine learning for your research data. assist you with the design of the data of experiments so that it can be used for artificial intelligence, and help you identify also opportunities to apply AI in your research or in your department. Okay, so I will show two cases today. So the first one is a project to automate the analysis of scanning electron microscope images. So this is a project we are doing with the group of advanced electronic materials and devices. Samira and Dorota are the research responsibles, and from the technical part, Francisco and myself are doing the machine learning implementation. So the idea is to automate the analysis of these images in order to extract more meaningful insights from this data. So the goal is they have a synthesis of graphene on copper, and so they want to identify when there have been a full coverage of the area with the graphene and where there has been some uncovered areas of graphene and you have the copper. In order to optimize the synthesis of this graphene, but the first step is actually to analyze the images to obtain some data to make a second step of a prediction algorithm. So basically we are doing this with deep learning, trying to learn how to recognize these faces, and then this will give us the input for the second stage to improve the synthesis. The way we work is with good software development practices. So we always do a repository in GitHub with a good structure, so it can be reproducible. You can follow all the steps of our trainings. We have a repository that you can find in GitHub. Right now, this one is private, meaning that only the persons inside the project can see it. I'm sorry. Do you know how can I move this? Okay. But when this is finished and published, the idea is that this is also public and everyone can use it. Okay. And the idea is this. So these are the images. So they have here so copper and graphene. And so for instance here, so we'll have the green is the graphene. So up to now they have been doing this manually with ImageJ, but this takes time and also is prone to errors or time consuming. So the idea was to automate this. So we want to make a deep learning to do this more in a high throughput. We started with 28 labeled images, meaning they have images with the true faces, the graphene, and some places where there is a second nucleation of graphene. But this is too little for our deep learning. So what we had to do was to build an application in order to label more images. So this is usually what happens with AI. So you need more data, and you have to go through manually labeling the data. So Francisco developed this, so you can do much more easily identify, let's say, what is the graphene, the first nucleation, second nucleation, and then use these additional images to train our model. So with this application, we added an additional test of 100 images. It was manually clicking along with the researchers and ourselves. So we extended the data set plus some techniques to do some image enhancing. So you can rotate images and so on. So to put it in your network so that it thinks that they are new images. So these are some of these. And at the end, with this app, the idea is that you have some buttons, so you can manually do much faster than with, let's say, the previous process. And also you have some already prediction of the faces. So we have a more or less decent model that can give you an initial stage of what is the graphene, for instance. And from there, you can improve or not. And then with this, the researchers now can start working with the data. If they think it is okay, they just click a button and this image can go through the database and enhance the model. Okay. And this is one example. So at the beginning, for instance, we had on the top, okay, here these are 3 different cases. So for graphene, so you have here the identification is not as good, but from there you can do some improvement. For some of the cases, the result of the machine learning is already pretty good, so you can really go quickly, and we can decide at which point this is good enough to go to high throughput. So this was one example. The other example was we are doing with the group of inorganic nanoparticles. They are doing catalysis and they synthesize nanoparticles. This is the group from Neus Bastos. So the idea was also to analyze these nanoparticles. So quickly, these are the images typically of platinum silver nanoparticles, and they want to characterize 3 parameters: roughness, check thickness, and porosity. Again, this is done manually. You can get some workflows on ImageJ, but the idea is to automate this to analyze this. So we built a tool that also was able to do a quick segmentation of the nanoparticles. Then the researchers can validate if this segmentation is good enough. And then from there, you can analyze all these 3 parameters. And then we can also do this high throughput. Okay, and the output is a database. In this case, is a column file that you can load into Excel and see all the parameters. For instance, this is for the last image. You have all the particles, the parameters, and then you can get the statistics, and then from there correlate to synthesis, parameter synthesis, so to improve the synthesis of the materials. This is, I wanted just to show you quickly how one of these apps work. So let me just show you here. So here we have this takes a little time. I don't know why. Okay, so this is one of the images. This is actually the tool. So the idea is that you choose the image, and then you go here, and then you can go to the next step, that is find particles. The first step is it does some bounding boxes of the object. This is similar to the models that use, for instance, intelligent cars and so on, that identify objects. Then the researcher can define if some of these are, let's say, doesn't correspond to a particle and delete it. You can also define some minimum and maximum diameter if you already know more or less what are the characteristics of your system. And then from there, you can go to segment the particles. So actually do the segmentation identification of each particle. Now this is an object that the software can identify, and now we can proceed to the characterization of this shelf, roughness, this thickness, and this is related to the synthesis and catalytic activity of the particle. And then you can calculate and save all the properties for this set of parameters. We have also participated recently in a hackathon using large language models, and we added somehow for fun, but also it can be useful. Okay, we added a button to analyze the results with a large language model, so it can go through all the files that have been analyzed and tell you this is the mean statistics of your files. You are missing some data from this regime or so on, and can help the researchers. So the idea with this that we want to give you is that there is a lot of potential inside ICN2 to really do, let's say, enhance and boost the research through data-driven approaches. But we need to work actually with the researcher, improve the data acquisition, and also improve how we generate and analyze these images. So all these tools can be helpful to have a high throughput data set to analyze lately with machine learning. I think that is what I wanted to present. Now I will give the site to Luis. And I will tell you, so you can find us through our mail. We are the artificial intelligence platform. You can contact us if you have some case that can be useful for your research, and we can be of any help. Okay. So I will now stop sharing and give. No. Already.
Oh, should I stay with Red here or let me see? I'm joining you. I think I was disconnected because yeah. Let's wait. Let's wait. Yeah. Que sí. ¿Qué quieres que haga?
Está ahí, aquí hay. Tenemos que. Cierra y abre.
Que vuelva a abrir otra pestaña o quieres que le dé otra vez aquí reset.
Sí, está aquí.
A ver.
Si no te comparto yo internet.
Yo creo que el problema no es. Ah, mira, ahí va. A ver.
Vale, ahora sí.
A ver. A ver. Sí. ¿Ya está?
Sí, ya está. Sí.
Okay. Okay, so maybe the first question is how much time do I have, Andrés?
So it will be 40 minutes.
40 minutes, okay. All right. Okay, so I will have to skip some of this. So first of all, thank you very much to the Institute for hosting me today. Again, my name is Luis. I come from the University of Waterloo, which is located in Ontario in Canada. I'm going to skip the part of, where we are and all that stuff because I don't have too much time. Basically, I am a professor in the Department of Chemical Engineering at the University of Waterloo. I hold something that is called a Canada Research Chair, which is basically like, basically in Canada, we get like chairs to do more research. I have one of those. And today I will be talking about some of the recent developments in my group to advance basically sustainable materials and energy systems, of course, in this era of the AI. So I'm gonna skip this because this is basically what we do in the group. Maybe I will just focus on this part at the moment. So these are the areas that I work in my group, right? All these areas basically are like my applications. So I have a lot of applications in biosystems and agriculture, CO2 capture and utilization. This is where I have done most of the work in basically materials design, computer-aided material design, which is this area here, optimal process integration and process intensification. So these are most of the things that I do in my group. These are the application areas, right? Now, in my group, I not only do applications, right? We also develop tools, theoretical tools that can be used to address, let's say, challenging problems, right? And for those, in this part, basically what we do in the group is that we use a lot process optimization. Of course, we now use machine learning. Most of the work that I do in my group involves dynamic modeling. So I like to do things in time or, like time forecasting models. And we also do, of course, a lot of multi-scale modeling when we basically try to couple multiple events that takes place at different times. So this is what we do in my group. And basically the idea in my group is to merge these two areas, right? And this is in a nutshell what we do in the group. I have, again, this is just an older version of my group of students. Now I have, I would say, new skin, and basically they are working with me. All right, so for this particular talk, again, I'm going to focus on materials design given the time that I have. I don't think I will have time to talk about the other two topics that I was planning on talking, which is chemical looping combustion and catalytic column design for biofuel production. In that particular area, I'm not specifically developed. I have developed materials particularly for this area, for CLC. We have designed oxygen carriers that can basically improve the operability of these systems. But again, I don't think I will have time to go over that. And of course, at the end, I will just give a brief outlook. So I don't think I have to sell you this. We know, I mean, in lunch today, we were talking about how, like our environment is changing, nature is changing. We are seeing events that we have never seen before, flooding, like a lot of fires, particularly in the, where I come from, in the north of Ontario, we have a lot of fires. This, was not in the news maybe 5 years ago. Now it's a hot topic, a central topic that we have to adapt to all these changes in the environment. Most of them, of course, come from global emissions, or basically greenhouse gas emissions. And of course, we have to do something, right, to try to alleviate all these issues, right? So these are just a few statistics that I want to show you as to how, of course, global emissions is affecting, right? Still, we rely on fossil fuels. Almost 60% of the global electricity comes from fossil fuels. We don't believe that is going to change soon. We still have a high dependency on those, so we need to mitigate those basically the use of these fossil fuels. Of course, when we use fossil fuels, we generate CO2, and part of what we do in my group is try to basically find ways to basically capture the CO2 and then use that CO2 for other applications, right? And in this case, of course, we want to develop and advance technologies for sustainable materials. So, as I mentioned, how to reduce CO2 emissions? This is just one way. Of course, you have the fossil fuel. You combust the fossil fuel in any way that you want. You are going to basically generate fuels and chemicals, and these fuels and chemicals will generate a CO2 that either you can take it and vent it to the atmosphere, or you can recycle it, right? You can capture it and then use it in some way. You can, of course, store it, and if you use it, of course, you can bring it back into the chain, right? And basically, you don't let this green loop to basically release CO2 either to the atmosphere or as a carbon storage, right? And that is where, again, we have focused in the group for many, many years, right? So in this particular case, there are many, many routes that can be investigated, right, to basically try to take this CO2 and then basically reintroduce it, to basically produce chemicals and fuels, right? One area, for example, could be for heat power and generation using for example, syngas, can be used, for example, to generate methanol, right, using one way. And if you want to generate syngas, which most of you know is just a combination of carbon monoxide and hydrogen, we need to transform this CO2 using, for example, thermodynamic catalysis, right, into CO, right, into the carbon monoxide. And this is what we've been focusing in this research. Obviously, if you produce methanol, this is the backbone of many, many processes that can happen in the can take place, right, in chemical and manufacturing industries. So this is the process that we focus on, something that is called the reverse water shift reaction. Basically, you take the CO2 that you capture from, again, fossil fuels, you combine it, for example, with hydrogen that could come from, again, an electrolysis unit or from a renewable electricity, and then you produce this reverse water gas shift. Now, the reverse water gas shift unit, basically the idea or the basic reaction is that you want to transform this CO2 plus hydrogen into carbon monoxide. And once you have the carbon monoxide, of course, you can produce the syngas. The problem with this reaction, right, in general terms, and you can use a catalyst, is that the reaction is high in energy, right? In order to do the transformation, I have to add energy, and by adding energy, of course, I incur in a lot of energy penalties, right? And that is where our focus is, right? Try to design new catalysts that can basically reduce this energy consumption or this energy dependence. And of course, we're trying to find a ways to make this CO2, right, becoming CO, but we need energy. And of course, that energy will come from fossil fuels. So the question is, are we really making a change, right? So if we're able to reduce this carbon monoxide dependence, right, we can transform this CO2 into, again, valuable chemicals and fuels. And that is the key idea here. Now, this is very slow. Okay, so if I look at the different chemicals or the different catalysts that has been proposed, in our group, we focus for quite a few years on these cerium-based catalyst materials, right? And if I take a look at the pure CO2 catalyst material, right, so which is this one, right, I will see that the conversion, right, of my carbon dioxide to carbon monoxide is very, very low, in the order of less than 10% at high temperatures, obviously. And the idea here is that what we want to do is that we want to dope the material, we want to design the new materials, right, using CO2 as the basis, cerium oxide as the basis, in order to basically increase the conversion, right? So in our group, right, for many years, UAU, which was my student, she actually did something that is called single dope materials. So basically, we dope the pure cerium with traditional transition metals. By the way, something that I forgot to mention is that I do modeling, simulation, and I do theoretical work. This work is a mix of theoretical work with experimental work. This is something that we did with Professor David Simakov in the Department of Chemical Engineering as well. So this is a collaboration, and also Professor Aping Yu from the Department of Chemical Engineering. So they are the experimentalists who actually are supporting the research. So all what you see here are experimental and modeling work, right? Of course, I took care of the modeling part and they did the experimental part. So as you can see here, we're able to improve the quality of improve the conversion by basically adding new materials or doping the cerium base with transition metals, right? So of course, the most promising material was iron, as you can see here, right? We also achieve almost the highest conversion, very close to the thermal equilibrium, or the ideal, the maximum conversion. But still, we got 100% selectivity. Copper got 100% selectivity, but we also observe low conversion. And basically, for cobalt and nickel, we observe high conversion, but with selectivity towards methane. All right, so of course, that produces methanation, and that is something that we want to avoid because we don't want to basically waste energy in separating further in the road the methane from the CO2. So basically, and that is the gap, right? This is still the gap that we would like to close, right? We would like to get as close as possible as to the theoretical optimum conversion that we can get. And this is the idea why now, of course, Yue completed her PhD a few years, I think it was last year. Now what we want to do is that we want to do bimetallic doping. What is the idea here? The idea is that instead of using, of course, one single dope, now I'm going to use two dopants. I'm going to use iron as the basic doping material, but now I'm going to use a subordinate, this M2, which is going to be basically another transition metal. And in our group, we try these different metals here, right? Cobalt, nickel, copper, and manganese. All right. So in this particular work, we have two types of objectives, or two objectives that we want to accomplish. Objective number one, we want to use DAS. That's the computational framework that we use in the group to do our DFT calculations. So with this DFT calculation, we're going to compute all the energies that we need to use to assess if a material can help us in reducing basically that energy dependence in the transition from CO2 to CO. And moreover, then we are going to use this as a tool to collect data, as I will show you in a moment. Objective number two, with this data that we're going to generate, we're going to design a computer-aided materials using something that is called reinforcement learning, which is an active learning method within machine learning. The idea here is that we want to accelerate basically the automated material discovery, right? And this is one of the central topics in my research nowadays. So let's talk about objective number one, which is the computational work. This is the DFT work. Again, it's for bimetallic doping. So before I get into the steps, I'm going to show you the steps that we need to follow. And I think this will be very important, right? So that you can understand basically what is it that we want to accomplish. What we want to do here is a formal analysis of basically all the energies that are happening, well, theoretical, from a theoretical point of view, that happen in the transformation of carbon monoxide into carbon dioxide. And there are many decisions, many degrees of freedom, as some of you know, right? So for example, right, if I want to dope the cerium surface, I need to, of course, locate, first of all, the dopant materials, right? I need to basically do oxygen vacancy first, sorry. And then I have to look at the different combinations, right? I have to look at, for example, I will only consider 2 atomic loadings, 4 dopant configurations. And basically, and of course, my dopant combinations are all the transition metals that I want to use. That will give me 32 degrees of freedom, all right? So of course, we have to take all this into account. Next is the oxygen vacancy. So basically now I need to choose one of these oxygens, right? And then replace that oxygen, right? Or remove that oxygen from my structure, right? And then of course check that the structure is still feasible, that is still robust, right? That basically is contained. And of course I need to calculate this oxygen vacancy formation as well. That is the second step. In this step, I have different sites that I have available, right? In this case, given my cell that I use, this is, by the way, the cerium oxide, as you can see. These are my dopants, right? This is M1 and M2. And basically, of course, I have 8 surface sites, so that will give me another 8 degrees of freedom in my system. In the next step, now I'm going to do the absorption, right? This is where I'm going to calculate the energy that basically the CO2 will actually absorbed in the surface. And as you can imagine, there are many decisions, also certain decisions here. I have 7 CO2 absorption sets. So basically, depending on the location of the absorption, that will give me a different energy. And of course, I have 2 different absorption configurations for CO2. That will give me another round or another set of degrees of freedom. And the last step is the CO2 dissociation. So now once the CO2 is being attached, now I have to deattach it so that I can basically release the CO2 and become carbon monoxide with hydrogen. All right. So these are all the steps that I need to follow, right? And the reason why I explain all these steps is because it's really important for you to understand the complexity in all these calculations, right? If you, for example, go and look at, again, at certain papers in material design that are doing computational work, particularly nowadays with reinforcement learning, some of those, they skip those steps, right? So here again, the idea is that we want to do this formal analysis. So I have different absorption sites, so that will give me another 8 degrees of freedom. So in total, right, if I were to do all these calculations, right, I will have to test more or almost 30,000 30,000 combination of all these degrees of freedom. That will give me roughly 2,000 DFT simulations. If I were to do only one single DFT simulation on just one single set of CPU, that would take me between 8 and 24 hours per simulation, right? Again, per one of these steps that I follow. And again, if I were to use only one computer, that would take me, of course, at least 5 years, right? Close to 5 years, assuming that everything works perfectly in an ideal world, which of course never happens, right? So this is one motivation to do the second objective, right? Obviously, we don't do that in this way. We have computers, we have GPUs, right, that can accelerate the internal calculations of DFT. And of course, we can use parallel computation to do this. Now, the other thing that we have to consider, and this is another aspect that, again, people typically, oversee, is that when you are calculating all these energies, right, sometimes, most of the times, people will actually choose the most stable energy. However, as we know in practice, in real life, that is not typically what it may happen, right? That's the idea, right? In some cases, you're going to have, for example, the most stable, right? Which is the one that has, of course, the lowest energy. And that will give you something that we call an upper bound on the reaction energy, all right? But we will also have the most likely, which is the one that basically will say, well, the CO2 will kind of absorb, but you don't want that CO2 to be strictly very, very attached to the surface because we know we have to pay the price in the dissociation. So this is something that we call the most likely reaction path. And finally, we have the most reactive when we assume basically the lowest energy, right? And that is, of course, typically sometimes unstable. So that is very unlikely to happen. Still, we want to calculate those energies. Now, what are we doing all this analysis? Well, we're doing all this analysis because we want to find, just by doing the computational work, which is, I would say, in general terms, the most attractive, I would say, bimetallic dope material that I can use to reduce, of course, the energy consumption in this transformation of CO2 to carbon monoxide for the reverse water shift reaction. That's the goal. That's the objective. That's what we pursue here. So if I look at the first pathway, and by the way, I forgot to mention this, we have 3 pathways. The first pathway, as I mentioned, is the most stable. So obviously, that will give me the lowest energy, in particularly the lowest oxygen vacancy energy, which is something that we observe will have a deep effect in the calculations and in the selection of the material. We will also have the lowest absorption energy, and of course, we are going to have also the lowest dissociation energy, which happens not to be spontaneous. Basically, what that means is that I have to add energy into the system, and this is, of course, where we pay the price. It's thermodynamically preferred, of course, because that is the most stable, but of course, we have a highest reaction energy, and that's what we call an upper bound. In the second pathway, right, we have, again, we use the most likely, which is the one that the CO2 is slightly absorbed. It's not the most stable, for example, it's not the most stable here, the CO2 absorption. And for that reason, right, we can get, again, the lowest oxygen vacancy, the lowest dissociation, which is still spontaneous, but we're going to have the highest CO2 changes in CO2 absorption, right? Again, that is where we think is absorbed, but it's not strictly super attached. Basically, it has an energy that I can detach very, very easily. And for that reason, as you can see, this delta is significant, and that is why we think it's the most likely configuration. Right, it's thermodynamically and kinetically balanced. That's how we define it. Finally, we have, again, the most reactive, right? This is where basically oxygen vacancy formation is positive, right? We have a high energy positive formation, which basically means we have to add energy, it's not spontaneous. We have the highest CO2 absorption, which again, in some cases is spontaneous, but in the case of the lowest CO2 dissociation, we observe that depending on the metal, we can have cases where basically we have to add energy, or cases where it's an spontaneous it's an spontaneous reaction, right? So that is something that we found that not so many people have reported. Again, depending on the type of pathways that you choose, this could happen. In reality, again, what we expect is that again is the most likely, but also the other combinations are possible. So this is kinetically preferred, but again, it's energetically unstable. Okay, so now let's look at the results. All these, you see points, but these are DFT calculations, right? This is DFT results. So the first thing that I want you to look at is this part, right? This one here is pure cerium, right? This is basically, if I do all these calculations with pure cerium, no bimetallic doping, I will observe that it has the highest oxygen vacancy formation. And that means that being the highest oxygen vacancy formation, it means that it's going to be very, very difficult to basically overcome that particular barrier, the energy barrier, right? So that is something that we observe. The other points basically are for the other pathways when we use, of course, bimetallic, and we also have here a single doped material, which is this one here. And in this case, what we observe is that there is a spontaneity, right? For this reaction pathway 3 is non-spontaneous for the oxygen vacancy formation for all catalysts, which again basically means that we have to add energy, but we already know that this is again the most unstable pathway. Is very, I would say, not so likely to happen, but we still want to take that into consideration, right? And of course, for pathways 1 and 2, we observe that all these, except for the pure cerium, right, are basically having, let's say, negative energy barriers, which is, of course, something that we would like to see because it's an spontaneous reaction. So if I were to focus then on my the 3 benchmarks, right? I'm going to neglect the pure cerium and the single dope because again, those have very high energies. I'm going to focus again on the bimetallic doping. So what we observe is that this material, right? We're going to use the 2 iron as a benchmark as well because it's just iron single double dope iron. What we observe, and this is the part that I want to get, is that this is the best material that we found based on this theoretical calculation, which is basically iron and copper, right? In cerium base. This basically what we observe is that this one has the lowest reaction energy, right? For P1 and P2, which are these ones here. But we also observe is that second lowest in this PY3. So basically this distance seems to be the lowest. And of course, the oxygen vacancy formation is spontaneous for this component, which makes it, of course, really appealing. All right. So these are the energy pathways that we found for this particular element. So let me just share with you some of the results. Again, for P1 is the lowest reaction energy in all catalysts, right? That's what we observe. The total reaction energy, right, is the second lowest for in terms of the second reaction pathways, but it's slightly above the benchmark. And for PY3 again, it's if in all of them, basically it has the lowest material, but is relatively high energy formation, as you can see here. And of course, this is detrimental. This is not something that you would like to see. Why did we do this analysis again? Because we want to consider all these reaction pathways when we make this decision, right? As to basically decide what is the best material. And of course, these are like the new results that we found. Now, the second best is this iron and nickel, right? And this one is because we have the lowest reaction energy, as you can see here, right? This is the lowest for the pathway 3. And basically, what I can show you here is that, again, this has positive energy, which again implies that we still have to provide energy. The oxygen vacancy formation is still positive. So again, there is still some requirements, right? But for this one here is the lowest CO2 dissociation, right, in all catalysts, and it's spontaneous for this CO2 dissociation. So that's what makes it a bit of attractive. And of course, it has a negative overall dissociation, which of course makes it really, really interesting because then it means that it can basically by itself, detach from the surface, right? Now, all these analysis again, we have to do all these simulations, almost 2,000 simulations, and basically that requires almost 5 years of simulations, right? Again, if we were to just do sequential calculation. So that basically opens the door to do something that we call human-in-the-loop reinforcement learning for this computer-aided design of materials. Okay, so for those of you who are not familiar with this tool, basically in general, and again, don't forget that I come from process systems engineering, we have to make different type of decisions, right? We have discrete and integer decisions. For example, we need to define the number of materials to test for catalyst design. In terms of scheduling operations, for example, I have to determine how many times I have to turn on or turn off certain equipment, or if I have to buy or not certain materials, right, from suppliers. Continuous decisions, for example, I have to define temperature, flow rates, pressures, and so on, equipment sizes, and loading batches. And for hybrid decisions, which is basically a combination of the two, I have, for example, to design, adopt catalyst materials that will meet certain properties. For example, in my case, I want to achieve something that is close to let's say, the theoretical conversion that I can get for a certain material. In general, what I need to do is, of course, I have to model the problem. I have to develop or adopt an algorithm. Of course, I would like to find a solution that we hope we expect to be optimal, right? So in my case, or in my work, we use, and of course, there are challenges in all this. For example, we have complex mathematical models, first principles, atomistic, that are very challenging to optimize, to simulate. The EFT is still, the computational costs are really, really high to do those calculations. So that is really challenging. We also have some mechanistic models that are very complex to solve. We're always subject to process and parameter uncertainty, right? Either endogenous or exogenous. And of course, solutions become obsolete. That's another issue, right? I mean, sometimes the chemical products and the manufacturing systems evolve, the materials evolve. So sometimes, of course, you cannot use the same materials all the time, right? And in this case, solutions, for example, actions are needed within a certain time limit. This is more for the applications in process control problems, where basically I have to decide an action and I only have seconds to make the decision, right? So it's some sort of like an online type of problem, right? So the time scale can vary from minutes to hours. Now, this is where, again, we have different type of machine learning methods, right? We use data to generate surrogate low-order models. We can have deep neural networks, support vector machine, k-means, I mean, different type of models, depending on the type of problem, the type of data that you have, if it's continuous, if it's integer, or it's a mix. We have different methods for prediction, supervised and unsupervised, but we also have this, which is active learning. And basically, these are methods which the key idea is that you don't actually need data. The data is generated by the method. Basically, it's labeled by itself. And that is the beauty. Something that, for example, like people also use in Bayesian optimization, all the data points are chosen, by the method itself. This is somewhat similar. In this idea, in reinforcement learning, basically, what we do is that we use reinforcement learning plus deep neural networks, and that gives us something that is called, of course, deep reinforcement learning. So for those of you who are not that familiar with reinforcement learning, the key idea is that you're going to have an agent, which you can think of an agent as a controller or an oracle, right? That basically will act on something that is called the environment. The environment is your simulation, is your environment. That's where you basically can design or can basically specify the problem that you want to solve. And basically this feedback, right, that happens, right, the environment is going to pass information to the agent is going to use that information to basically design new actions on the environment or test new actions on the environment. And based on this learning procedure, right, based on this feedback, the agent is going to learn. What is it going to learn? It's going to learn the model parameters. Don't forget that this agent is just a deep neural network, right? Or any type of architecture, right? Could be, for example, an LLM. Nowadays is, it's more, it's kind of a hot topic nowadays to use LLMs as the agent, but could be anything, right? So in very brief terms, what this loop is doing is that the agent is trying to find the optimal parameters in your neural network that will maximize a reward function. That reward function is your objective. That's what you want to accomplish, right? Let's say I want to maximize conversion. In some way, you have to define that within the environment. And I say in some way because it's not a very direct correlation, right? There are many, many implications in doing that. I will not have time to discuss all those, but designing that reward function and designing this feedback is key for the success of this method, right? At least in my experience, right? So for example, again, I can design a product, a catalyst given a set of candidate materials, which is what we are doing in this work. And that is the whole aim here, right? I want to design an agent that is capable of telling me what are the optimal materials that I can use, for example, to minimize the total reaction energy. Instead of me doing all these simulations, I want this agent to do it online, all right? At the end of the day, this framework design a policy. What is a policy? Again, is your deep neural network, and the parameters of these networks are optimized. What does that mean? That if you provide states to that policy, those are, you can think of those states as your inputs, then it's going to give you an action. So for example, if you want to say, I want, find me the optimal material that will achieve a certain energy, this particular agent should be able to give you, again, that material. All right, in very simple terms. Okay, so I'm going to skip this for the sake of time. We have done a lot of applications in my group. As I mentioned, I not only do material design, I do a lot of work in process systems engineering. I do a work in chemical process optimization, scheduling. This is an area where we are exploring deeply the application of reinforcement learning. This is where I think that it might have a big impact. Reinforcement learning, molecular design, we have done a few works. Dynamics and control, like using basically reinforcement learning to do control, and also for optimal process flow sheet design, which is kind of molecular design, but of course, instead of designing molecules, we design processes, right? And we use, I don't know how familiar you are with Aspen. We use basically Aspen or HYSYS to basically do this design of my flow sheets. So in this particular work, what we did, and again, I'm going to tell you a bit of the story, is that back in, I don't know, like 2 years ago, 3 years ago, with my colleague in the Department of Computer Science, Professor Pascal Poupart, and his group, and of course, through our collaboration, right, back in those days, Shiram was also a postdoc in the group. Now, Shiram is a professor, an assistant professor in Carleton University in Canada. We decided to say, okay, let's try to do the standard reinforcement learning, right, to basically design this material. And what we found out is that this process was very, very intensive and it required a lot of time. Okay, so this was not being, giving us result at the speed that we wanted. So for that reason, what we did is that, again, we decided to do our own version of reinforcement learning, something that we call human in the loop. So in our case, of course, the environment is VASP, is where we do the simulation. So as you can imagine, calling VASP to do all these calculations will take a long time. Okay. So this is what we developed, which is something that is called the human in the loop. What is this idea in human in the loop? I'm going to have an agent. And again, don't forget that the agent, all what it wants is to find the optimal parameters in my network. And if I let it run, eventually, hopefully, it's going to learn something or it's going to design my network, but it will take a long time. So what we're going to do is that we're going to give them basically some help. And this help will come from a human. And all what the human will do is that it's going to introduce a binary decision as a feedback to the agent, right? The human is going to say, this particular material is good for whatever objective you want to accomplish. In our case, of course, designing the bimetallic, or is not good. Why? Because maybe it's expensive, because I cannot synthesize that in the lab, for any reason, right? So basically, you have to basically provide these binary decisions. How does this work? This is a bit of math. I'm not going to get too much into that, but basically, it's a distributional reinforcement learning, which instead of looking just at a single value, we're going to look at a distribution of my entire domain. And based on this distribution, I'm going to sample from it. And of course, I'm going to choose the value that is, closest to the mean value. But in this case, since we're using this human in the loop, we're going to have two functions in the reward function. We're going to have our regular standard reward function that is going to take care of course, the agent. But we're going to add another term in my reward function. And basically, this additional term is coming from the human. And this human basically is no other thing but designing a neural network. And this neural network is going to basically learn the feedback from the human. All right. So through this feedback, we are going to basically design a new function, and this function is going to be inserted into our reinforcement learning framework. By the way, we have a manuscript ready for submission in this work, or we already are in the process of submitting this work. So the whole idea again is that now the human computes a human score is sorry. Let me go back. The human basically scores a binary decision. This binary decision is going to be used by the network, right, or by the neural network to learn this kind of information. We don't have to, of course, it's random decision, right? In this case, the human is going to decide which are the experiments that he wants to use. More like, of course, what you want to have is sensitivity. You want to have positive results and negative results, or good and bad materials, if you want to put it in that way. And basically, we're going to design that network, right? And it's parameterized, of course, by certain parameters. And the whole idea is that now we want to use this network, and we're going to introduce that network as part of our reward function, right? And through this network, we observe that this is going to, of course, accelerate the training. Why? Because now the reinforcement learning will have this additional piece of information that can use to make a more effective sampling or efficient sampling of the data. All right. We tested this method, or we are currently testing this method on a very simple problem, right? Which is basically trying to get this structure here and try to find let's say the best single doped material, right? That can basically absorb hydrogen on the surface. This is what we do. Of course, we're still using BASP. We also combine with quantum espresso now. Nowadays, we're actually using some databases and some networks that are available in the literature to basically estimate all these prediction properties. So we're replacing the BASP with some structures, some machine learning structures that are available. All right. Now, what we observe, and this is just, again, we compare the performance of this hydrogen absorption on nickel 1-1 surface. And what we observe is that we basically compare this against the benchmark, the best performing benchmark available in the literature that was called EXPAND. And as you can see, number one, this is us, right? We were able to learn more and more effectively. Basically, this is the reward function. In this case, it's the absorption energy. And what we observe is that we were able to get to this point in a bit faster. The training process went from days again to weeks. Okay. All right. How are we doing with time?
Okay, we have 10 more minutes.
10 more minutes? Yeah. Okay. So let me just maybe touch on this. This is the second part of the talk. So now I'm going to show you something on basically packed bed reactors in chemical looping combustion. This is not on materials, right? This is more again at a macro scale level. The idea in chemical looping combustion is that you have an oxygen carrier, right? Which is basically again a metal oxide typically, right? And what you want to do is that on one section you want to oxidize it, and when you oxidize this material in the presence of, for example, of oxygen or air, you're going to get heat, which of course you can use that, for example, to supply that to for energy. And what we do with this oxidized material is that now we're going to reduce it using a fuel. So that is where the reduction process takes place. And now we generate carbon dioxide, or a pure stream of carbon dioxide and water. And this is basically where we capture the CO2. So the beauty of this chemical looping combustion is that you get the best of two worlds. Number one, you generate power in some way, in this case through heat. And you also basically capture the CO2. And once you capture the CO2, of course, you can reuse it, reutilize it for many applications. Why CLC is an intensified process? Because of course this happens, there are many different ways that you can run this loop, this oxidation reduction, fuel flexibility. You can use different type of materials. In my group, for example, we have used biomass-based materials, typical fossil fuels like methane, and other type of fuels. You can even use liquids. I haven't explored liquids yet. I'm mostly focused on gas. And again, biomass materials. You reduce NOx emission. By the way, the key idea, I forgot to mention this, the key idea in this CLC is that you don't want to mix the oxidation stage with the reduction stage. So in between these stages, you always have to purge. And you want to purge because you don't want these NOx emissions coming from air to be mixed with the reduction, because then you're going to have here NOx. And of course, what you really want to do actually is avoid having additional elements here that will require an additional separation stage. That of course requires energy. So there is a potential for negative emissions. There are some discussions. So what we have observed is that there is between 30 and 50% reduction in capture cost when compared to the typical post-combustion CO2 capture. Now, if you have a CLC island, right, and a CLC island is a bunch of these packed bed reactors. So this is my oxygen carrier at different stages, right? Purge, reduction, oxidation, purge, and so on. You can again provide heat or provide basically the power to run a gas turbines, right? But you need to have an island, right? So one question that you need to do, first of all, again, there are different configurations. In this case, I have PBRs, packed bed reactors, right, that have no solid recirculation. It's good for high pressure operation. It's a more compact reactor, but there are many challenges. Of course, there is a dynamic operation because you do reduction and then you do purge, you do oxidation, and so on. You need to run multiple PBRs in unit, and of course, you require sophisticated control and scheduling strategies. That is the part that we focus in this work. So in this case, this is just one single unit. So on one side, of course, I want to basically produce a highly pure CO2-rich stream using the fuel, right? And once this bed is reduced, I'm going to switch to oxidation, where now I switch from fuel to inert and air. And now I want to basically generate the heat that comes from the oxidation process. So for each one of these, I need to design controllers. I need to design basically optimal controllers that will allow me to do these reactions. So I'm going to focus just on the oxidation part. So in this case, basically, I have a control variable, which is the outlet temperature, right? I want to control this. I have two manipulated variables that I can use for controlling the process, the air and the inert. I have multiple constraints, which is, for example, I want the outlet temperature to be below the safety threshold, right? And of course, I would like to at least achieve 95% conversion of my bed. So we also have another issue that basically, motivate the need for this, the application of reinforcement learning. We have partial observability. What does that mean? I cannot observe all the states or all the things that are happening in the system. So I can only pass part of the information to the agent or to the controller. And of course, I also have a delayed action response. What does that mean? That when I pass the air, there is something that is called a hotspot, right? Like a temperature front that basically is moving right through the bed, and then at the end of the day, I'm gonna get a very high temperature at the end. This is the optimization problem that I would like to solve, which again is an optimization problem that will take a certain amount of time to solve. And this is where I need to make certain decisions, right? And I need to solve this problem online, because at every point in time, I need to provide an action. I need to basically tell the operator how to move these valves, right? So solving this problem online, again, is expensive, and that's what we want to avoid. Moreover, this model, as you can imagine, is very complicated. You have a lot of, you have more than 75 states here, and that takes, of course, a lot of time. So let me just go very quickly through this. I'm not going to spend time on this. This is my reinforcement learning framework. Basically, we are designing now an agent. The agent becomes my controller. Under partial observability, basically, I assume that I can only observe certain states of my systems, the one that I can measure, for example, temperature, and certain concentrations at the outlet. And I need to design the reward function. And perhaps this is the more challenging part in reinforcement learning. How to design this reward function nowadays is still an art, right? You just have to do a lot of trial and error. This is what we came up with, and this is what we observed that it worked. So let me just get to the results very quickly. So this is the training curve that we observed. So as you can see, again, we reach a stability, which reach a plateau at the end of the day. The training time, and this is where you pay the price, was almost 11 days. But once you train this network, now you have, again, a policy, an agent, a network that can basically give you results in the order of microseconds. So now my policies, right, which are these ones here, I can get each one of these policies. Basically, I can tell the agent, given these inputs, the temperature in the system, the concentrations, and so on, tell me what is the action that I need to take. That action basically can be done in less than a microsecond. That is the advantage, right? Basically, we move this online computational cost to make it offline. And now I have basically an online network that can give me policies that I can implement online in very short computational times. Now, what we did here is that we tested under a more realistic scenario where we basically say, okay, I'm going to assume that I don't know everything. I don't perfectly know my parameters. So in this case, for example, I put noise in the outlet temperature. I assume that I have a measurement that is noisy. And as you can see here, basically this light blue represents the variability in the output basis, of course, because this is validation. We did it, I think, for 1,000 runs. And as you can see, I remain within, on average, I stay within my set point, my desired set point, which is of course positive. And then we do it under catalytic deactivation. So that's another thing, right? Of course, the oxygen carrier, right, changes, right? The morphology changes. There is degradation of the oxygen carrier. So here we assume that there was the, the activation of the carrier. We assume multiple levels of, deactivation. And as we observe, of course, the larger the activation, of course, the shorter the reduction time, the oxidation time. But still, my policy was still able to maintain my production of power and near optimal points, right? So basically, this is telling you about the robustness of the policy that we designed. Okay, so with this, I think I'm going to skip this part. I think I would like to stop here. Let me just go to the end very quickly. I just want to acknowledge again, of course, all the people who have given me the support to do this research. Sorry for all this. Again, I have other projects, right? I will not be able to go. This is the part that I would like to get. All the projects on material design, for example, the one that I showed you at the beginning comes from the Bank of Montreal. This is one of the, I think is the top, one of the top 5 banks in Canada. And of course, I have a lot of collaborators, MyTax, which is a non-for-profit organization, Canada Foundation, the Canada Researchers Program, and of course, NSER, right? And more other organizations. I also would like to acknowledge all my group, my research group, that throughout the years, of course, they have done the work, and of course, I am nobody without them, right? So again, thank you very much for the information. This is my email. This is my research group on LinkedIn, which I have seen that now is more used by academics than by people looking for jobs. So if you want to also contact me through LinkedIn, you're more than welcome. Thank you very much for your time. And of course, if there are any questions, I'll be happy to take them. Okay, thanks.
So now we have time for questions.
Sorry for I won't be on the time. So. Yeah.
So very interesting is well, neural models. I'm an electrochemist, and I'm wondering if you could, instead of using temperature, use other parameters like electrochemical potential and these type of things to like feed the system and then help with the decision making.
Yeah. Something, of course, for due to time limitations, I couldn't talk too much about this. But one of the beauties of reinforcement learning is that it's a model-free method. What does that mean? That the environment that I show you, that box, could be anything, right? Anything that gives you data. Could be experimental data, could be a table in Excel, could be a very sophisticated model like, for example, an atomistic simulation like BASP, could be whatever. So for that reason, you can design a reward function that will accomplish the objectives that you want. And for that reason, we are not limited, right? To basically choose, limited to or restricted on, on the variables that you would like to observe and improve, right? So the straight answer will be yes, it can be done. Mind you though that again, designing that reward function is not straightforward, okay? What I typically like to tell is that my student spends most of the time designing that reward function. Once they know how the reward function, how basically the agent learns, right? Then, of course, that learning that the students get for them is easier than to design new reward functions that will accomplish different goals. But in short, it can be done. Of course, we have to do the work, right? So, and again, most of my students, that's where they spend, a fair amount of their time at the beginning of the research, right? Like designing that reward function and testing many things. But it can be done, yeah.
Okay, so I also have a question regarding the reward function, how does it look normally? Mathematically, is a computed expression or?
No, again, that's the beauty, right? I mean, sorry, let me just go back here. As I show you here, this is the reward function that we use for this case, right? Again, getting to this reward function took, not even days, right? Weeks, months. In this case, my student, Ola Ali, she's the one working on this. She was working with one of my current postdocs, Daniel, who did his PhD with me. Daniel had a lot of experience in basically his thesis. His PhD was on reinforcement learning for scheduling applications. So he had experience. So then, both Ola and Daniel worked together. But basically, Ola did the heavy lifting and she designed this reward function. As you can see, for example, again, this is not just saying, give me basically the optimal temperature, right? You have to design this reward function with certain care. For example, due to time limitation, I didn't talk too much about it, but as you can see, there is an exponential term, there is a k here, which is a parameter that we have to define. There is an overhead penalty because if you don't want to go beyond a certain temperature, so we have to penalize that. So this is the way that you have to impose constraints. There is a bonus, for example, we give them a plus, for example, if we see that certain temperatures are achieved according to the way that we want it. So again, this is where I believe this is still an art rather than a systematic method, right? It will highly depend on your specific needs to tackle this.
And on your expertise on these systems, which are the advantages and disadvantages regarding intensive data? How much maybe you have to use more data, less data to gain the same precision or objective function that you want compared to simply, let's say, as you say, just saying, let's optimize the temperature and let's run Bayesian optimization or deep learning.
Exactly.
So in your experience, which are the advantages of this reinforcement learning? Because you have then the cost of this defining of the.
Exactly. Okay, so that's a good question. What I will say is the following. If you have a tool, for example, if I go back here, right, this problem here. If you, for example, we have solved in my group, we have solved this problem and we have presented papers where we show the implementation of this, right, for online applications, right? What is the problem? The problem is that sometimes this problem takes not minutes. Well, doesn't take, let's say, 5 to 10 minutes to give us an answer, for example. Again, I'm just putting an example, right? Whereas the actual process demands that you need to provide an action in seconds. All right, just to give you again a sense of the orders of magnitude. So that is where these techniques fail, right? Or may not be, specific. Now, of course, there are ways that you can reduce the complexity in the problem here. Instead of making it a highly nonlinear problem, you can make it linear. You can linearize the problem, and by linearizing the problem, of course, you solve the problem faster. You solve the issue on computational cost on one side, but of course you lose accuracy, you lose performance because now you're using a linearized version instead of using the realistic model, right? So if you already have a problem, and for that problem, let's say the straightforward solution works, then I would say don't change it, right? This reinforcement learning, in my opinion, is done for cases where the problem is complex, where you don't know too much about things, where you say, you know what, my problem is not fully deterministic or fully stochastic, it's a combination, or I have a combination of data with a model, or I have very, very specific conditions, right? Or I want to accomplish many, many things at the same time, right? That is where I think reinforcement learning is really useful. Of course, the training, designing that function is still, the time-consuming part, the art, in my opinion. Okay. Now, don't forget that this loop, right? In this loop, you don't generate the data, right? The data basically is labeled by itself. And that is one of the problems with reinforcement learning, that the agent basically is something that is called sampling inefficient. It's not very good in doing effective sampling. And of course, there is an ongoing research in how you can make this one more effective, right? That is still the main bottleneck in, in reinforcement learning, right? That is the reason why it takes long for this agent to learn, the environment, of course, to learn the reward function and to optimize the reward function, okay? But yeah, I mean, the beauty of this is that basically this environment could be anything. right? It's a model free, so could be data, could be an Excel file that you have all your, your spreadsheet, for example, could be a lookup table, could be a highly complex model that, you simulate in bus, lamps, whatever, or could be data that is coming from those simulations, which is what we do. You can impose as many constraints as you want, right? There is no limitation on that. But again, you can do whatever, you can do many things here. The problem is, yes, you can do it. But now how do you transfer that information to this guy? Through the reward function, the states, and so on. That is what makes this problem challenge, right? In designing this reward function, in my opinion. Okay. But what we have seen is that once you design it, once you get a policy, that policy is really good. Of course, depending on your goals, right? It's really good because now in seconds or less than a second, you can get an answer to your problem, right? Of course, as I mentioned, right? In my case, we are moving this computational time from being online to make it offline. That's where we pay the price, right? As I mentioned here, right? It took us almost 11 days to train this guy, the agent, right? But once I have the agent, now I basically I give them what are my states, and this agent will tell me what are the actions to do in less than a second. That's the advantage. All right. So that's the reason why I think that for online applications is really good, right? This type of network. With this human in the loop for the materials design, we're also observing that it's accelerating. In that case, we're not interested so much in the online. We're more interested in getting to this point faster, because we know that it's not going to take days, it takes weeks or months to get those results, right? So that is what we are aiming in that case. Yeah.
Any other question?
Yeah.
Just
Yeah.
Thank you for
Yeah.
presentation. Just a curiosity. In the work on reverse water gas sheet, you were mentioning the CO2 dissociation as
Yeah.
part of the process.
Uh-huh.
I don't know if you need to consider, for example, the hydrogen absorption and
Okay. That's a good one. No, here I'm assuming an ideal environment where there is no other species but the CO2 being absorbed and then the CO2 being dissociated. And of course, when it dissociates, it forms the CO and then the hydrogen, right? But I'm not looking at the hydrogen. If we were to add, we can add it. That will add more degrees of freedom. That will make the problem even more complicated. That's the reason why I wanted to explain the steps that I did. Because again, if you go to the papers, you will find that people can claim that they do these calculations. However, when you actually go and read the papers, it's not very straightforward in the way that they calculate. They use some which is fine, right? They use some assumptions, right? Maybe their point is not to do some detailed computational analysis. It's more like illustrating a framework, for example, which is fine. But in our case, we're interested in getting, let's say, results, right? Like results are coming from, let's say, all these analysis that we do. Yeah. No, but in that case, yes, we can add it. We didn't do it because we wanted to reduce the computational costs. Yeah. In previous work, we have done it, right? I mean, for example, in the case of methane, many years ago, we have to do all the dissociation of methane, right? Methane becoming, like CH3, CH2, CH, and C. And then each one of these species will react in the surface, will create other things, and so on. And then it becomes a highly complex, set of reactions. Yeah. But it can be done, yeah.
If not, there are no more questions. I want to thank again Luis.
No, thank you for your time. And if there are any further questions, I'll be happy to answer.
Yes,
Thank you.
And Luis will be here so for the rest of the afternoon and tomorrow. If you have any other questions, you can contact me and
Yeah.
we have a talk. Thank you.
Okay, thank you. So should I stop sharing now? Can I close my? I can leave, right?
Yeah.
There's a meeting. Okay.